So this problem is only tedious. It's not very difficult. However, we do need to do a lot of calculations, and there's a lot of room for computational errors. So definitely just be careful. Let's start. The angular momentum. The formula is going to be I omega, and we can say that the um, angular momentum of the sun is going to be I omega, but I of the sphere omega. So this is going to be equal to 2 times the mass of the sun, radius of the sun, squared, divided by 5 times 2 pi over the period of the sun in its orbit. So we can say that L of the sun equals 2 times 1.99 times 10 to the 30th. And these are all tabulated values, so you simply need to look in any physics textbook in order to find these values. Times 2 pi. I apologize, the 5. Clean this up. And this will be divided by 5 times 25 days times 24 hours per day times 3,600 seconds per hour. And we have the angular momentum of the sun being 1.12 times 10 to the 42nd kilogram meters squared per second. So in order to find the formula, the moment of inertia for all the planets, well, the planets are in orbit with the sun. So the center, an axis going through the center of the sun, that would be the axis of rotation here. So the distance between a planet to the axis of rotation would simply be the distance from the planet to the sun, and these are tabulated. So we can say that L of Jupiter is going to be equal to the mass of Jupiter times the radius of Jupiter squared times 2 pi over the period of Jupiter. And again, this term right here, r sub j, simply means the distance from Jupiter to the sun. And this is going to be equal to, we don't need the parentheses, so we can just say 2 pi 190 times 10 to the 25th kilograms, 778 times 10 to the 9th meters to the squared, divided by 11.9 years times 365 days per year times 24 hours per day times 3,600 seconds per hour. And this is going to give us 1.92 times 10 to the 43rd kilogram meters squared per second. The same thing is going to happen for Saturn. So we'll say L of S, the angular momentum of Saturn, equals the mass of Saturn times the distance from Saturn to the sun squared times 2 pi over the period of Saturn. And this is going to be equal to 2 pi, 56.8 times 10 to the 25th, 1,427 times 10 to the 9th squared, all divided by the period of Saturn is 29.5 years. So we're going to have to do 29.5 years times 365 days in 1 year times 24 hours in 1 day times 3,600 seconds in 1 hour. And we're approaching 7.81 times 10 to the 42nd, rather, not over anything, my apologies. Simply the units, kilograms, meters squared over seconds. So at this point, we are going to do the same exact thing for Uranus and Neptune. So this will be the mass of Uranus times the radius of Uranus squared over 2 pi divided by the radius of Uranus. Rather, 2 pi divided by, my apologies, the period of Uranus. This is, again, the angular velocity of Uranus. So this will be 2 pi, 8.68 times 10 to the 25th times 2,870 times 10 to the 9th squared divided by, this will be 84 years, times 365 times 24 times 3,600, and we're approaching 1.69 times 10 to the 42nd kilogram meters squared per second. And then finally, angular momentum of Neptune, mass of Neptune, distance from Neptune to the Sun, squared times 2 pi over the period of Neptune. 2 pi, this will be 10.2 times 10 to the 25th, 4,500 times 10 to the 9th squared, divided by, here it's going to be 165 years, times 365 times 24 times 3,600. And this is going to be 2.49 times 10 to the 42nd kilogram meters squared over second. And so if they're asking us for the angular moment, the kinetic energy, the rotational kinetic energy, rather the total angular momentum of the solar system and the percentage of the total angular momentum of the solar system that is accounted for by the rotation, by the planets rotating the sun, we're going to simply take the angular momentum of the planets and divide it by the angular momentum of the solar system. And this will be equal to L of the Sun plus L of Jupiter plus angular momentum of Saturn plus angular momentum of Neptune plus angular momentum of Uranus, and then angular momentum of Jupiter plus Saturn plus Neptune plus Uranus. And I'm not going to write down all of these numbers because they're already down here. So you can simply add them up and divide it by the sum of the total angular momentum of the solar system, and you find that this is equal to 0.966. So 96.6% of the of L solar system equals L planets. Essentially, 96.6% of the angular momentum of the solar system is accounted for by the rotational energy of the planets orbiting the sun. So again, it's tedious. However, it's not hard. You simply have to make sure that you don't make any computational errors. And that's the end of the solution. Thank you for watching.